Okay, welcome to revision 2. Here we'll talk about drag force and terminal velocities. Okay, I'm going to start off by doing a question. So this one, drag force, is given by this equation. Do it yourself lah. Show that C has no units. I think this one I can leave it to you. Let me know if you need help. Okay. So a raindrop falls vertically from rest. Drag force is the air resistance because you travel very fast. But initially, we assume the air resistance is negligible. So sketch a graph to show how time and velocity of the first 10 seconds of the motion changes. So if you remember this equation, V equals to U plus AT, the raindrop is free falling if there's no air resistance. So I'm just going to put 0, 9.81 and 1 here. So you can see that after 1 second, the speed would have increased from 0 to 9.8. or 0 to 10. So in 1 second, I'll go from 0 to 10. Okay? I'll draw around like slightly under 10. Okay, so then you're asked to calculate the velocity of the raindrop after falling 1000 meter. Sure. So your S is 1000, T you don't have, U is 0, V you want to find, and A is positive 9.81. Treating downward as positive, okay, so that your S can keep as positive. So since we do not have, see the arrow there, downward is positive. No T, we'll use V square is U square plus 2AS. Okay, so sub the values in, and you will get a very large speed, my friend. 140 meters per second. So fast. Okay, but of course cannot reach this fast lah, because in practice the air resistance is not negligible. So because there's drag force or air resistance, and drag force is state an equation relating drag force acting on the raindrop when it's falling at terminal velocity. You know airplane terminal. So terminal velocity is when the velocity doesn't change. So some of you actually ask me what I intend to draw in my notes when I say a parachutist jumping off this graph lah. I intend to draw this graph. I'll draw it here for you. Okay, so this one, parachutist falling from an aircraft, is shown. Okay, I'll go through part by part in the graph, and this will probably take a while. Feel free to pause anytime. So you can see at point A, the beginning part of the graph, it's a straight line. Straight line because the raindrop or the parachutist is just falling down. So the predominant force here is mass, because the value of the drag force or air resistance is very small. Just only fall the speed is very slow. Okay, and the acceleration is about constant, so you kind of get a straight line in the beginning. And then when the gradient begin to become less constant or begin to flatten out, this is when your velocity is large enough so that now your drag force D is significant. So if I'm going to draw mg like this, okay, so let's compare. You can see this D is quite small. Okay, then D becomes bigger and bigger because the the parachutist is falling faster and faster. Now, D will increase until it's equal to mg. Now, once it's equal to mg, there is no way that it can travel faster anymore. Equilibrium, mg equal to d. So BC is what we call terminal velocity. When mg is equal to d, the net force is 0. So your acceleration is 0. Okay? So when you're transitioning, right, from A to B to C, when the gradient begins to decrease, it's because the net force decrease, acceleration decrease. Now at point C, sudden changes happen. This is because the parachute opened, the drag force increased a lot. So you can see D suddenly just blew up, increases rapidly. So because of this, your net force went from 0 to upwards, very large upward net force. So the parachute will slow down very quickly. Okay, slow down rapidly at where I draw the blue line. All right, and then finally, right, at point D, okay, the drag force will decrease because you slow down already, so your drag force has begun to slow down decrease again. So at DE, it's slowing down. So your D will decrease back. And because your D decreases again, your drag force decreases again, the acceleration will decreases in magnitude. So the gradient is getting less steep. It's the same idea. Okay, just like in the beginning, when you open the parachute, the acceleration increased, but the magnitude also increase in opposite direction. Now finally, you notice after E, it flattens out because yay, D equal to mg again. So your drag force decreases back such that it is equal to mg. And once again, you will get your terminal velocity. Okay, so at positions of terminal velocity, I will highlight here. And the idea of terminal velocity is because your acceleration has decreased to 0. Now this is a family favorite to us in objective. Sometimes they ask in structure. But the concept of it is very important. So if you're confused with this, arrange to come and see me, okay? So in the beginning, you can see drag force very small, increase until the speed can no more increase because it balances off the mg. You have a high terminal velocity. I kind of don't want to die. So we'll maintain at BC first. And then after that, it will drop. Okay, it's going to drop very fast because when you open the parachute, drag force becomes very big. So your speed will begin to decrease again. So your speed will decrease until your drag force decreases together and you reach terminal velocity. So we're going to define some stuff, or just to fill in the question. We define acceleration as rate of change of velocity, and Newton's first law will be an object will not change its state of motion unless acted on by an external force, aka the law of stubbornness. You won't change until you got external force. Okay, so let's see. Calculate the distance traveled by the parachutist in the first 3 seconds of the motion. So in the first 3 seconds, right, we know distance is area under the graph, so we're going to just super zoom in. So only nice thing about having a digital paper is you can zoom in. 3 seconds. So this scale is a little bit odd, but not very odd. It's just they label every 2.5 boxes. So 3 cm, so in the middle between, so I think this is 6. It's like 1 cm is 2. So you'll notice that all the graphing is a bit cha-cha. Okay, so 3 cm is somewhere here. I'm just going to extrapolate here so that I can get a value. Because this looks like a triangle to me, thankfully. If not, we have to count boxes. I'll do an example where you need to count boxes later. Okay, so we're dragging it upwards. And I think at 3 seconds, I will nicely hit 30. Okay. So yeah. So it will be half times 30 times 3. Area under the graph. And that, my friends, will give me 45 meters. All right. Okay. Explain the variation of resultant force. Only talk about the force, don't talk about other stuff, unless you're explaining why the force is like that. So at t equal to 0, which is point A, the resultant force is very close or equal to mg, and it's constant. The weight of the parachutist. Okay, this is because, don't forget, you have to explain the drag force is small or negligible due to the slow speed or the small velocity of the parachutist. Okay, then when your speed is large enough, so as v increases, because don't forget the thing is free falling, you will encounter more and more drag force. So drag force increases, your resultant force decreases. Okay, because they're in opposite direction, it decreases until point B, because point B is where it flattens out, where it is equal to the magnitude of the weight. So when drag force is equal to the magnitude of weight, resultant force from B to Z is 0. So my sentence could be made better if I if I just add a point at point B, drag force is equal to the magnitude of the weight. All right. So resultant force from B to Z is 0 as both speed and drag force remains constant. So I'm going to show you roughly where the marks are. If you say the resultant force is constant and equal to the weight because drag force is negligible, there is 1 mark. If you say drag force then increases because the speed increases, and because of this resultant force decreases, that's the 2nd mark. And then you say at point B, drag force is equal to the magnitude of weight and resultant force is 0. This is the 2nd mark. So the resultant force is 0. Speed don't change, drag force no change. Okay? Same thing happens after you open the parachute. Drag force too big, you slow down, drag force decrease until equal mg. Same speed. You can land safely. Anyway, describe the changes with the frictional force on the parachute disc at 15 seconds. So increases suddenly at a large magnitude because you open the parachute now. Okay, so between 15 seconds, the friction will decrease because you already slow down. Anyway, mass of the parachute disc is 95 kg. Calculate the average acceleration and the average frictional force between 15 to 17 seconds. Now, my friends, 15 to 17 seconds, again, hi, good thing it's a straight line. It looks like a straight line. I shall assume it's a straight line. If you have actual physical paper, you can put your ruler there and check whether it's a straight line or not. But online, so you can use a ruler or a tool. If you're wondering what I'm doing, I'm trying to find 15 and 17C. Okay? And I'm trying to read the graph. So the whole idea of having a parachute is to suddenly increase your drag force to slow you down, such that when drag force decreases and d equal to mg again, it will be at a lower speed. And then you can be safer, and you can just do it again. All right, anyway, 17 is somewhere at 20, I think. And 15, now you can see the pens I use. I tend to show the extrapolation because some syllabus requires you to show it, but A-levels, they're not that strict about us checking whether you indeed read from the graph. But you can also make it a habit. Anyway, it looks like 15 seconds, it will be almost precisely at point C. And that is actually, I think, 50 meter per second. Alright. So you kind of like decelerated from 50 to 20 in 2 seconds. No bad. So you can use A is gradient, or V minus U over T. So 50 to 30 divided by 2. Negative I put outside because decreasing, so the gradient is negative. Okay, so 50 minus 20 divided by 2. Think I'll get negative 15 meter per second square. Okay, to find average frictional force, I'll use F is equal to ma. Let's consider the forces. We have drag pointing up, we have mg pointing down, and the acceleration is negative upwards. Upwards is negative in this question. Okay, slowing down. Upward is negative, downward is positive. Alright, anyway, you just take mg minus d is equal to ma. So can just find d here, negative 15. If we're treating up as negative, because the parachute already open, so your acceleration has to be upwards. Then you slow down as you fall downwards. Okay. Later I'll show you what happens if you flip the sign convention. Okay, so you'll get 1860, I think. Oh, yeah, I made a mistake. I thought the parachute disc is 75 kg because I'm thinking of Asian weights, you see. But actually, it's Angmo weights, 95. Okay, so correct already lah, this one. Anywho, If let's say you use f equal to ma, but you flip the signs, meaning you take up as positive, down as negative, okay lor. So you have d minus mg is m a, d which will be ma plus mg, which is 95, my bad. I don't know why I keep thinking he's 75. And then the a and g, 15 plus 9.81, because we're treating upward as positive. Get the same answer, okay? All right. So based on this understanding, we can write the equation for the forces acting on the raindrop when it's falling at terminal velocity lah. You will have the so-called friction or drag force. Now I'm checking here to see what, okay, they also use D for drag force. Use the symbols that they give, you don't invent your own symbol. It is different for every question. So you have D and you have pulling upwards and mg pulling downwards. So at terminal velocity, d equal to mg, where m is equal to mass of the raindrop. I tend to define any symbols that is not mentioned in this question, just in case. Okay, you have the mass of the raindrop, cross-sectional area, density of air, and the initial velocity of the raindrop is 0, value of c is 0.6, show the terminal velocity is 7. So I'll give you so much numbers, confirm it's a substitution question now. So you get d is equal to mg, and you can substitute the whole chunk on top, c rho a v square is equal to mg, because at terminal velocity d equal to mg. So you rearrange, you get this equation, then you substitute, making sure everybody is SI. You know, whenever you substitute into a physics equation, especially if it involves a physical constant like 9.81, it's like doing a photo shoot for the family. You have to make sure everyone wear nicely. You have to make sure all your units convert to SI. Okay? If you're not sure, just convert. Better to dress up than to dress down. Better to convert and not need to convert than forget to convert but need to convert. All right. So 3.77, so sorry, 7.33 meter per second. So it's about 7. So the raindrop reaches terminal velocity after falling about 10 meters. Now draw, sketch the variation of Vt. So you expect the plateau to happen at 7, not 10. You cannot reach 10. Drag force doesn't allow you to reach 10. Too bad. Raindrop. So I'm going to take 7, okay? I assume I cannot plot 7.33 lah. How to plot? So 7 is here, okay? Then I got a slight problem lah. I know that it will be a curve following the shape of the graph that I showed you just now. I just don't really know where the 10 meter will be. So if you check the area under this graph, right? The graph that of the straight line, the triangle, this area is 1 times 10 divided by 2 is about 5. So whatever area under the graph before I hit terminal velocity, it should be double the area of the triangle. Ish. Double-ish. So you don't go and, this one is definitely too soon. So no. Need to go stun. Later. Maybe need to be severely later. Okay, so you need to travel 10 meter, double this area. So because this area is only 5. Area of the triangle is 5. So you kind of like need to, okay, again, I'm going to keep redrawing it until it looks correct to me. Okay, so again, the area under the curved portion should look about double the area of the triangle. I'm just estimating. Anyway, it's 2 marks. So 1 mark is when your terminal velocity is 7. And because the time is very big, so the time for you to hit Vt is between 1.5 to 3.5. Pretty large. Anyway, you cannot really tell the time. when it hits terminal velocity because you don't have enough information. All right, try some objectives. I will see you in the next part. We'll talk about work, energy, and power.